Welcome to tonight's video on Unit 4, Part 3, talking about composition and inverses of functions. So in the last video, we talked about how to combine two functions. That was f plus g, f minus g, f times g, f divided by g. But now we're going to talk about how to compose one function of another, and that's what the f of g stands for. That means f composed with g. That means basically you take the g function and you're going to put it in the f. And to find the domain, you must find the domain before you simplify the f of g, meaning you got to take into consideration what the domain of the g function is first, or the one that you're putting in. So for example, in part A here, it says find f of g of x. So what I would do first is I would rewrite it using parentheses. And then we're going to work from the inside out. So we're going to substitute in the g function. And then that square root of x plus 2 is going to go into the f function everywhere you see an x. So it's going to be the square root of x plus 2 squared minus 1. Now from here you must consider the domain of the square root of x plus 2. So the domain of g here is that it must be greater than or equal to negative 2. Now we can go ahead and simplify and see what the domain of the simplified is. So we square it, we get x plus 2 minus 1. So we get x plus 1. Now, that is f of g of x. However, the domain for f of g of x, since this is all real numbers, and this is greater than or equal to negative 2, it would be greater than or equal to negative 2. So basically, it's the intersection of those two. Because you have to take into consideration the restriction here on the square root of x plus 2. Even though when you square it, it becomes x plus 1, you still have to be able to substitute it in the g function first, then the f. So for part B, to find g of f of x, the order does matter. So that means you're going to take the f function and put it in the g function. So f of x is x squared minus 1. There is no restriction here. So then we take x squared minus 1 and then add 2. So we get the square root of x squared plus 1. Now x squared plus 1 can never be negative because you can't square a number and add 1 and get negative. So therefore the domain of g of f is all real numbers. All right, the next one for part A, f of g. So that's going to be f parentheses g of x. So that means we're going to take f of the square root of 4 minus x. Now we also have to consider that the domain of g here has to be less than or equal to 4. So then when we simplify f of the square root of 4 minus x, we get the square root of 4 minus x squared plus 4. So it's 4 minus x plus 4. It's equal to negative x plus 8. However, the domain of f of g is less than or equal to 4. So for part B, doing g of f of x, we get g parentheses f of x, which is equal to g of x squared plus 4. So there's no restriction on x squared plus 4. We put it into the square root, so it's 4 minus plus 4. We have to distribute the negative sign. So you get the square root of negative x squared. And so when you square a number, it's always going to be positive. So when you take the opposite, it's going to be negative. The only number that won't be negative is 0. So the domain for this, domain of g of f, is 0. All right, for number 3, you're working backwards. It gives you the composition, and you're trying to find the two functions. Remembering that the one that comes second, so in this case the h of x, goes inside the g of x. So basically the h of x is the inner function, and the g of x is the outer function. So the inner function, what's underneath the square root, that is x squared plus 3. And the outer function is negative 2 times the square root of x plus 5. That's the outer. So another example, if I told you that f of x was 3 times the absolute value of x minus 2 plus 7, you would say h of x is equal to x minus 2, because that's what's inside the absolute value, and g of x would equal 3 times the absolute value of x plus 7. So that's how you do those problems. So next page has some concepts, like for example the concept of an inverse, the notation. So if it's just an equation where it says y equals, then the inverse would be y inverse. But if it's defined as a function, then it's f inverse of x. The negative 1 power means inverse. The concept of what an inverse is, an inverse just undoes the other one. So for example, if f of x equals x plus 2, the inverse, what undoes that, is x minus 2. Some concepts to think about when you take a value of the function, like 1 plus 2 equals 3. If you take the value of the inverse, so 3, notice you get 1. So the point 1, 3 is in the function here, but in the inverse it's 3, 1. Notice the x's and y's switch. So that happens for inverses. The x's and y's switch. So this process is how you would find an inverse, and we'll go over that when we do some problems in the next section. This is what we're talking about here with the x's and y's switching. So if I know the domain of the equation, that's the same as the range of the inverse, and the range of the equation is the domain and the inverse. Basically the domain and range flip for the function and the inverse. To determine if the inverse is a function, we can do the horizontal line test, which says if a horizontal line intersects the graph of an equation only one time, then the inverse equation is a function. So basically, if you look at a parabola, yes, it passes the vertical line test, so it's a function, but it doesn't pass the horizontal line test, so the inverse would not be a function. Doesn't mean it doesn't have an inverse, it just means the inverse is not a function. And if the inverse is not a function, then the function itself is not a one-to-one function. In order to be a one-to-one function, basically the function and its inverse are functions. So that means the original function must pass the vertical line test and the horizontal line test. Because inverses basically undo each other And the original function is always x, right? So if you add 2 to x, then you subtract 2 for the inverse. Like here you multiply 2 and subtract 3. Here you divide 2 and add 3. So because x is the original or identity function, when you do graph inverses, they should be symmetric to the line y equals x. And to prove two functions are inverses, this is where the composition comes in. If you do f of g of x, it equals x. And if you do g of f of x, it equals x. Yes. So those are some rules for functions. So now we're going to do some problems here. The first one, part A, says state the domain and range of the equation. So the domain of y, and remember, underneath the square root has to be greater than or equal to 0. So it's going to be from -4 to infinity. The range of the equation, well, remember, any square root has to be positive or 0. So it's going to be greater than or equal to 0. Which means for part B, when you find the domain of the inverse, that's the range of the equation. So it's going to be greater than or equal to 0. And the range of the inverse is going to be greater than or equal to 4. So for part C, you can sketch a graph. So first we can graph the equation. So if I put -4 in, I get 0. If I put -3 in, I get 1. And then the next perfect square is 4, so I'd have to put 0 in. And I get the square root of 4 is 2. So your square root function is going to look like that. This is y equals square root of x plus 4. The line of symmetry is y equals x. So it's just a diagonal line going through the origin. Like that. And then the inverse, remember, I don't even need to know the equation. I can just flip the x's and y's, so it'd be 0, -4, 1, -3, and 2, 0. So this is y inverse. So we'll come back to that graph in a second to do some of these, but, well, actually we'll do it for this one now. For part D, is the function 1 to 1? So does the original graph pass the vertical and horizontal line test? Well, it passes the vertical and it passes the horizontal. So yes, y is 1 to 1 since it passes the vertical line test and the horizontal line test. So therefore it would be 1 to 1. Find the inverse. So remember, this is where the process that we talked about here, right here, comes into play. So the first thing you want to do when finding the inverse is you want to switch the x's and y's. And now you want to solve for y, so that means I have to square both sides. And then subtract 4. So that is your inverse. Now the only thing you have to keep in mind is that there is a restriction on the domain here. It has to be greater than or equal to 0. So there you go. So that is your inverse for part E. For part F, it says prove that they're inverses. So f of x is equal to the square root of x plus 4. and g of x will be x squared minus 4. So you need to do f of g of x and g of f of x. So when you do these compositions, so here you put g of x in, and that means it's going to go into the f function. So it's going to be the square root of x squared minus 4 plus 4, which is the square root of x squared, which is the absolute value of x, but it's still x, absolute value or not. So g of f of x, so this f of x is the square root of x plus 4. And then we put the square root of x plus 4 in, so it's going to be the square root of x plus 4 squared minus 4. So it's x plus 4 minus 4, which is x. So f of x and g of x are inverses since f of g of x and g of f of x both equal x. All right, and then last but not least for part D, it says find the points of intersection of the equation, inverse, and line of symmetry. So notice right around here is where all three of them intersect. So we're going to find the point that occurs. Well, remember, that's y equals, so we're going to do g. So that's y equals x, square root of x plus 4, y equals x, and y equals x squared minus 4. So all three of those intersect. So what I would do is set them equal. So I'd set like the square root of x plus 4 equal to x. And I also could set the x squared minus 4 equal to x. And see if it's in the same spot that they intersect, y equals x. And in this case, notice when I square it, both sides, I get x plus 4 equals x squared. So I get 0 equals x squared minus x minus 4. And if I did the same thing here, subtract the x, notice I get the same equation. So as long as I solve this, I get the intersection. Well, there are no factors of -4 that add to -1. So I have to do the quadratic formula. So the opposite of -1 plus or minus the square root of -1 squared minus 4 times 1 times -4 all over 2a. When you simplify, you get 1 plus or minus rad 17 over 2. And since when you look at the graph, it intersects in the positive side of the x-axis, it's actually only 1 plus the rad 17 over 2. So the point of intersection is 1 plus rad 17 over 2, 1 plus rad 17 over 2. Because remember, it has to intersect the line y equals x, so that means the y and x coordinate are the same. All right, so last one, number 5. Part A, we want to find the domain of f of x. So domain of f is, well, we know for a fraction, the denominator can't equal 0. So it's going to be -infinity to 2, union 2 to infinity. For the range, the range of f, well, you want to figure out what y can't equal. Well, to figure that out, you look basically, if you were to take the limit as x approaches infinity of the function observing highest powers, notice you get -3. So that's what y cannot equal, is the limit. So y can't equal -3, so therefore it has to be from -infinity to -3, union -3 to infinity. So for part B, when I do the domain of f inverse, it's going to be from -infinity to -3, and -3 to infinity, and the range of f inverse is from -infinity to 2, union 2 to infinity. All right, so then it asks you to graph these. So we're going to first graph the function. Remember, it's a fraction, so there's going to be a vertical asymptote at x equals 2, because remember, wherever the denominator is equal to 0, you put a vertical asymptote. There's a horizontal asymptote at the limit, which is y equals -3. There's your horizontal asymptote. Now, if you put in some points, like for example, if you put in x equals 3, if x equals 3, then y equals 10 over -1, so -10, which means there's a point down here. So that means it's going to follow the vertical asymptote and follow the horizontal asymptote like that. Then if you look at x equals 1, when you put it in, 3 times 1 is 3 plus 1 is 4 over 1, so it's 4. So the point 1, 4 is on 1, 2, 3, 4. So that means it goes up this way and down that way. So that's the function. Now remember, the reflection is y equals x here. And now if we look at the graph of the inverse, remember, you're just going to switch the x's and y's. So if we find that, or if we use that philosophy, all right, so since x cannot equal 2, there's going to be a vertical asymptote at x equals 2. And since y cannot equal -3 in the original function, there's going to be a horizontal asymptote at y equals -3. So we can put those on the graph. So here's x equals, there's x equals 2, and y equals -3 is right here. That's the vertical asymptote and the horizontal asymptote. Then when we put points in, like for example, if we put 3 in for x, 3 times 3 is 9 plus 1 is 10 over -1. So it's -10. So 3 -10 would be a point on the line. And it goes towards the horizontal asymptote that way and down towards the vertical asymptote. That's what the asymptotes do. If I put 1 in, see 1 is the next number over from 2. 3 times 1 is 3 plus 1 is 4 over 1. So it's 1, 4. And 3, -10. So same thing, it's going to go towards the vertical asymptote here, horizontal asymptote there. So that's the graph of the function. Then remember, you want to graph the symmetric line, y equals x. And then the inverse, well, the inverse, you just switch the x's and y's. So instead of a vertical asymptote at 2, it's going to be a horizontal asymptote at y equals 2. And instead of a horizontal asymptote at y equals 3, it's going to be a negative 3. It's going to be a vertical asymptote at negative 3. So there's our vertical asymptote x. And then you switch the x's and y's. So instead of 1, 4, it's 4, 1, which is right here. And then notice it's going to go towards there and towards there. And then 3, negative 10 becomes negative 10 and 3. And then it goes towards the horizontal asymptote and towards the vertical asymptote. And notice, so you got a reflection there. If you notice, they're all kind of in a line. So the answer to the question in D is it 1-to-1? And the answer is yes, because if you do the vertical line test and the horizontal line test on the original function, it passes the vertical and horizontal line test. All right, so now for part E says find the inverse. So the function is 3x plus 1 over 2 minus x. So to find the inverse, first I'll make f of x y. Then remember, you switch the x's and y's. So now I have to solve. Well, let's first get rid of the fraction. So it becomes 2x minus xy equals 3y plus 1. So then I want to get all the x's on one side and all the y's on the other. Well, I'd actually want to get everything with a y on one side. So let's move this xy over. So, and then we'll move the 1 over. So you get 2x minus 1 equals 3y plus xy. And the reason why I did that is so I could factor out the y here, and it becomes 3 plus x. So then you divide, and notice you get 2x minus 1 over x plus 3 equals y, and that is your f inverse. That is the inverse of the f function. So that is part E. As far as part F goes, proving that they are inverses. So remember, f of x is going to equal 3x plus 1 over 2 minus x. G of x is going to equal, the inverse is going to be 2x minus 1 over x plus 3. So now we have to do f of g of x, and we have to do g of f of x. So f of g, so we put the g function in first, so the 2x minus 1 over x plus 3. So that means everywhere there's an x in the f, so we go 3 times 2x minus 1 over x plus 3 plus 1 over 2 minus 2x minus 1 over x plus 3. Looks kind of ugly, but let's distribute first and then we'll get like a common denominator. So multiplying by 3, I get 6x minus 3 over x plus 3 plus 1 over 2, and then when I distribute, well actually here we'll wait to distribute the negative, so minus 2x minus 1 over x plus 3. So then get a common denominator, so it's 6x minus 3 plus x plus 3 over x plus 3. And then here it's 2 times x plus 3, so 2x plus 6 minus, and now you can distribute the negative, minus 2x plus 1 over x plus 3. And so we'll combine like terms first. So we get 6x plus x, because the 3's can't, so you get 7x. So 7x over x plus 3 over, and then the 2x's cancel here, over 7 over x plus 3. So basically when you multiply, you divide, you multiply by the reciprocal. So notice the x plus 3's cancel and the 7's do, and you're just equal to x. Yeah, sorry. So now we gotta do the other way, the g of f of x. So we put the f function in here, so we get 3x plus 1 over 2 minus x, and then we put that everywhere we see an x here, so 2 times 3x plus 1 over 2 minus x minus 1 over 3x plus 1 over 2 minus x plus 3. Multiply by 2 first, so you get 6x plus 2 over 2 minus x. And then if you get the common denominator of 2 minus x, you have to distribute the negative, so you get minus 2 plus x. And then here, you get 3x plus 1, and then you get the common denominator, you get plus 6 minus 3x over 2 minus x. So then notice the 2's here cancel, so you have 7x over 2 minus x. And then the 3x's cancel, so 7 over 2 minus x. And notice when you divide, you multiply by the reciprocal. So notice those cancel on the 7's, so it's just equal to x. So yes, f of x and g of x are inverses since f of g of x and g of f of x equals x. All right, the last thing we have to do, part G, is determine determine the point of intersection. So remember, we set them equal to x, so 3x plus 1 over 2 minus x equal to x. And we also, so we can set that equal to x and find out where it intersects. So notice if we multiply here, by 2 minus x, both sides. Cancels the fraction, so you get 3x plus 1 equals 2x minus x squared. So bring everything over. So you get x squared plus x plus 1 equals 0. So you can't factor, but when you solve the quadratic formula, you get negative b plus or minus the square root of b squared minus 4ac all over 2a. So notice you get negative 1 plus or minus the square root of negative 3 over 2. So that means there's no, because it's I rad 3, that means there's no real solution, which means they don't intersect. So you could say f inverse and y equals x do not intersect. You showed that algebraically. You could tell graphically, because if you look at the graph that we created, notice they don't intersect the line y equals x. But we did want to prove it algebraically, but we can check graphically to see that that is correct. All right, so that concludes our video for this evening. Hope you have a good rest of your evening.